Hello, everyone. I'm really glad to be here, be able to share a little bit more about our work. And I would, of course, like to organize the organizers for inviting me to be part of this class. All right, so, 3.5 years ago, I had just finished two big projects. One of them was AlphaCode, the other one was AlphaTensor. I'll tell you a little bit more about those in the future. But basically, during the Christmas holidays in 2021, I stumbled on this talk from 2019 called The Future of Mathematics. And the talk is over an hour. The comments were extremely positive. One person was saying, this is the best lecture and the best YouTube video ever. I've never watched anything more enjoyable. So, I was pretty intrigued and I pressed play. And it started a chain of ineluctable events that basically takes me here in front of you today. So in this talk, rather than focusing on the details, I'd really like to focus on the big ideas that allow us to work on AlphaProof and why we believe it has an integral role to play in the future of mathematics. I will basically talk first about the rise of formal mathematics and what that is, then about our experience in reinforcement learning and the lessons we've took away, and how these two things meet with AlphaProof. So Galileo said quite a long time ago that the laws of nature are written in the language of mathematics. It was an incredible prediction or insight because we've made a lot of progress since Galileo. And indeed, now just a few equations on a single page can describe how the universe works extremely precisely. Also, in a famous essay called The Unreasonable Effectiveness of Mathematics, Eugen Wigner argues that mathematics not only have like a descriptive power, but also have predictive power. One example he gives, if I'm not mistaken, is the development of matrix algebra and its use in quantum mechanics. Of course, once you can describe and predict the natural world, you can start to shape it. And if you look around us, in the world we live in, the civilization, the culture, all the tech, that makes our current world, well, basically mathematics is just at the core of everything. And maybe I would also like to argue that mathematics is a root node to intelligence. So root node is a word that Demis really likes to talk about. And basically, it means that from that root is going to blossom a whole tree of possibilities. And why could we argue that is because mathematics requires reasoning and planning, generalization and abstraction, knowledge and creativity, open-ended and unbounded complexity. And over the years, I also understood that mathematics is not just this kind of application of logical rules one after the other. It's really a sort of art, and so it even requires an eye for beauty. And so I used a lot of keywords here, but you'll see them reappearing during my talk, and I hope that will make these a bit more concrete. In summary, I've tried to convey to you that mathematics is a root node to understand the natural world, but it also might be a root node for intelligence. So I think it's worth kind of really thinking about mathematics and see what can we do for that. But before that, I'd like to give you a really super brief history of formalization in mathematics, because basically mathematics hasn't always looked the way it looks now. About 500, before Christ, the Greeks had a great revelation. They understood the importance of the concept of mathematical proof. And in some sense, can you really imagine, it's like you find something that will tell you with certainty that you have attained kind of eternal truth, and you can discover more and more truths of our universe. It must have felt incredible. And since then, proofs is at the heart of mathematics. And what constitutes a proof, however, has evolved over the millenniums of mathematical history. One of the first breakthroughs, I'm sure that is with Euclid and his book Elements that have definitions, axioms, and theorems. And so that's really kind of the start of axiomatization. But that has really kind of been developed much more in the early 20th century with Hilbert program that really developed this to land on what we have now. So that's kind of axiomatization on one side. On the other side, like mathematics, at the beginning, it didn't really use symbols. And that's for a very long time, even if the Greeks had kind of find axiomatization and started to use some symbols, the rest of the world kind of describe really mathematics with a lot of words. And so here you have like a square and 10 times its root equal to 39. So today we would write this as x squared plus 10x equals 39. But look at this description of how do you solve this thing. Take the coefficient of the root, divide it into two parts, and multiply one of them by itself, add this to 39, etc., etc., right? Now you just write kind of this concise kind of formula. And there are two things here that comes, is first, replacing kind of, using special, I don't know, like in the machine learning lingo, using special tokens for numbers, right? Like we represent like the digits have special kind of characters. But also even more important, well, I don't know which one is more important, but that helps with also kind of, I think only in the 17th century, René Descartes kind of comes up with the idea of using kind of the early letter of the alphabets to denote constants, and the end of the letter of the alphabet, X, Y, Z, to describe unknowns. And so that's basically how you end up with this formula. But it takes, like, I don't know how many, it takes until the 17th century to really come up with those notations. And I think it's not hard to argue that precise notation and axiomatization really eliminated ambiguities and logical error, that symbolic notation made complex manipulations more tractable and requires much less, cognitive load. It also kind of packs information extremely densely. In terms of notation, I can't remember exactly who said that and if it was a joke or not, but someone was arguing that maybe the Einstein notations was his biggest contribution. That might be pushing it a little bit with given like the impact of general relativity, special relativity, and even his work to introduce quantum mechanics. But certainly kind of Einstein notations are very important. And actually, if you read machine learning code, you'll see that appearing a lot as well. But basically, once you have those symbols and you can lift yourself up from kind of particular examples, you start to be able to observe different common patterns across different contexts. And so that's where abstraction and generalization comes up. You can unify disparate areas of mathematics. And actually, you can even create new fields. And so my favorite example here is really the people who are looking at the 5 axioms of Euclidean geometry and actually, I don't know, for thousands of years, I think, trying to see if they could remove the 5th axiom. And that actually led to non-Euclidean geometry, and in particular Riemannian geometry, which in this theme of general relativity was essential to get general relativity. So this formalization has helped mathematics, but also the other sciences, in particular physics. And so I would like to argue that basically computer formalization, which basically means writing mathematics in code, is just the next logical phase in this grand arc of mathematical formalism. So there's been quite a few languages to describe mathematical reasoning, such as Coq and Isabelle, and Lean is one of the most recent ones, originally developed, I believe, for software verification, but also with mathematics in mind. And mathematicians saw in Lean kind of the tool that would make the next big step in mathematical formalism. So it's a programming language, it's a theorem prover, an interactive proof assistant. Lean has a really vibrant open source community of mathematicians. And it's been used to formalize like cutting edge mathematics, field metal mathematics. And the mathematicians are on a huge quest to basically build the math library of the future. So let me go there. It's called MathLib. It's built open source on basically the free time of mathematicians. And it has two big goals. It aims to be general and unified. So general, it means that it has the weakest assumptions and the strongest results. And unified is that it only has one definition per concept. So I was actually pretty surprised when I learned about this unification idea. Because I thought that mathematics was written in a very structured way already, but apparently it turns out that for a given concept, you may have several papers that basically talk about the same concept, but that define it in a different way that is not necessarily compatible with each other, and so you need to do quite a bit of work to actually kind of try to find the unifying definition that underlies all those ideas. And so that's actually what takes the most time in building MathMe. Maybe you can see, in the representation I gave here, that it's one monolithic library where everything is connected together. And so this is very important for modern math, because basically modern math is about kind of trying to connect all areas of math. And there's been observations that actually, like ideas from here can help ideas from there. And for instance, maybe Fermat's last theorem's proof is a great example of this, connecting two different areas to try to prove one huge theorem. Now there is also something called the Lang-Langs program that really explicitly tries to do that and connect all these areas. So it's really important that you have a library that basically can connect all different areas of math. Currently, the library covers about 80% of the undergrad curriculum. And most of the library, however, is above the undergraduate, but has a lot of, or irregular coverage and big holes. I think particular examples are complex analysis or PDE theory. Okay, all great, but why do all of this, right? Is because computer formalization unlocks kind of enormous synergies. And maybe to explain myself a little bit, I have to step back. And for those of you who are coders, maybe like just understanding the right code and be able to use all the software stack, that should be already a huge win for mathematics. But basically, the other property of when you write mathematics in code with those languages such as Lean is that you get perfect verification. So when you write a proof and you write the correct proof, Lean is going to tell you, yes, this is correct. And when you've made a mistake, Lean is going to tell you, your proof is not correct or is still incomplete. So from these two things, you get some instant wins. First, your correctness concerns completely disappear. You can trust giant proofs, and you can delegate proof checking entirely to the computer. And so I think it's important to note, and it's my understanding, that it's not like all areas of mathematics are suffering from concerns about correctness. I think in reality, most maybe areas where mathematicians feel pretty comfortable about their ability to discern, correctness from mistakes. But I've been hearing that in maybe some of the areas that are more abstract areas, actually they start to be real concerns for correctness. So that's not everywhere, but that starts to be important. So these are the instant wins. But those, perfect verification and software stack has really kind of a knock-on effect that could lead to game changers. So first, I think for all of you who are coders, to bring all the tools that we have developed for coding should already be a big win. Next, I have transformed mathematics into a video game. So what does this video game look like? Well, what are the levels? The levels are the different theorems. And then, you can interact in those levels. And basically, kind of Lean will tell you, yes, you've completed the level or not with this perfect verification feedback. You always have harder level. And maybe contrary to other games where maybe, I don't know, you have to shoot other people, this is a super meaningful, useful, and profound game. You're basically adding new truths for eternity. The Lean people describe this as they could do this 14 hours a day, and they're constantly getting positive reinforcements. This also means that it's great for education. First, like a lot younger people now are really used to using computers and softwares, and it's great because it's interactive, right? When it's fun, it's easy to learn, and you can also create kind of software such that like the detail of the level of detail is adapted to the person who is reading, rather than the level that the author thought was interesting. I don't know if you read a lot of math papers or you look at solutions of some problems you are trying to solve. Sometimes people say, well, this next step is quite obvious, but maybe it is not for you, and you'd love to see more detail. I have also an example from my dad, who recently tried to learn kind of Galois theory in a different online class. And so he went through week 1 and week 2 and week 3, all good. But then when he was going through week 4 and trying to do the homework, he realized that there was something he didn't understand, and he basically needed someone to explain to him. And he messaged the professor, but unfortunately the professor didn't reply. And so he was basically completely stuck. But imagine that instead, he was doing this in Lean, then Lean would have said exactly, what is right, what is wrong, what is missing, etc. And he would be able to have like constant feedback without having to ask his teacher. And now I want to go to the last point. It's actually a point that has been made by Terry Tao, I think, about a year and a half ago, at least. And he describes that basically using computer formalization will unlock massive collaboration between mathematicians. And so why does he say that? Well, apparently the current state of mathematics kind of collaboration is that you can do, most of the papers are either single author or two author paper, and kind of the max is really 5 author papers. And the reason why is because every author needs to check everyone else's work. And so basically kind of having more and more collaborators doesn't really scale because you still need to check everyone else's work. And so that's where like kind of computer formalization and perfect verification comes in, is that if you could trust the computer to check the proofs, then suddenly it opens up kind of working on in mathematical projects to, I don't know, thousands of people, because you could have someone you've never met who lives in the middle of nowhere, who contributes a little bit to your proof, a lemma there, and then Lean will say, yes, this is correct, and then you can just move on, right? And so there's been kind of there's been a few projects like this. I think MathLib is maybe one of the coolest demonstration, where you have hundreds of mathematicians working together to build this library of the future. But I think Terry Tao is also arguing that you could use that to do new mathematics. And has actually launched a project in the past called Universal Algebra, where he was exploring that. But basically, like I think in ML at the moment, we are all about scaling. And here, basically, you could scale humans to do mathematics and potentially maybe tackle harder problems. All right. So, should everyone go to, computer formalization? It's awesome. The reality is that there are still challenges for computer formalization. In my estimates, about only 0.1% to 1% of mathematicians have adopted Lean. It's a small community of mathematicians, vibrant one. But why is that? It's because it's actually not yet a great tool for mainstream research. Like a lot of, programming languages, it has a steep learning curve. It also requires a significant time investment because, to get perfect verification, you need to be able to write every single detail. And so, that takes a lot more time. Maybe that's not the place where you want to focus. You want to focus on the things you don't yet know how to solve, not on the things that are more obvious to you. And so that will be improved as the tooling and the library matures. But at the moment, there's still some things missing, and obviously, there is also a passive lack of necessity for research. But I'm hoping that the arguments I've outlined in the slide before are going to change a little bit that point. So now I just want to show you a little bit what it looks like. So this is a proof that you may know about. It's called. It's about how many. It's about proving that there is an infinite number of primes. Okay, so this is what it looks like in Lean. I hope you can see that it's big enough. And so, oops. Okay, here it is. This is the theorem statement. And I think what is kind of remarkable is that because you can use Unicode, it looks pretty much what you would write yourself on a piece of paper. Says that for all n natural numbers, there exists a p, such that p is bigger than n and p is prime. So that's one way to say that there is an infinite number of primes. This is what the proof look like, so fairly compact in this case. And the fact that you can understand all of this is because basically Lean is a language-based high-level syntax and mirroring normal mathematics. So let me go a little bit on what it looks like to interact with this thing. So here is the first line of the proof, and this is actually the main insight that Euclid had, is to consider first n factorial plus 1, and the mean fact of it. So what is the mean fact? Is the mean factor of n factorial plus 1. So I want to draw your attention on the box on the right there, called the tactic state. And so basically that's what Lean returns to you. It says, oh, here are the things we know, and here are the things we still need to prove. So we know that n is a natural number. We know that p is this mean factor of n factorial plus 1, and you still need to show that there exists a p such that p is bigger than n and p is prime. So let's go second line. Second line says, oh, let's prove that n factorial plus 1 is not 1. And you have actually the proof in line with maybe a few more characters than you really want to prove something this easy. But on the right, you see that you have a new fact in your arsenal, is that n factorial plus 1 is not 1. And then we're going to say, now let's prove that p is prime. And the proof is say, well, is because it's basically we took the minimum factor, right? The minimum factor is kind of, it's obvious that it's a prime, unless the thing you've taken off is 1. And so that's why you have this thing you needed to prove before. And then kind of the proof continues. And at the end, you should see in your tactic state no goals. And it used to be, I think, in a previous version of Lean, that you'd also received kind of this tada emoticon. And I think, unfortunately, it's been removed from the current version of Lean. But basically, it's your little reward for completing this level. So just to recap, right, computer formalization, there is a really vibrant community that has a huge enthusiasm for this. They are building the library of the future in their own time. It has many ways in which it can unlock enormous synergies, but it still has some way to go. And this community and myself as well, we have the belief that this will inevitably play an integral role in the future of mathematics. Just this work kind of pushed the computer formalization. All right. So now I want to talk about some concurrent development in AI and focus on something that was extremely popular a few years ago, got forgotten a bit in the last couple of years, and now is making a comeback big time. So hopefully, like you've picked up on my hints with this little reward, this environment, this interactiveness, this video game. I want to talk about reinforcement learning. So what's reinforcement learning, also known as RL? Basically, it's just trial and error learning. It's a very general framework of an agent trying to achieve a goal. So really, this agent learns by interacting with an environment to maximize a reward. And I think there is sometimes misconception about this reward. It has to be very dense, or it has to guide you towards a solution, etc. Not at all. In the framework of RL, the reward can be basically, have I achieved my goal or not? So basically, in RL, we really need to have a goal. But then your reward can be goal achieved equal then 1, otherwise 0 all the time. If you don't really have a goal that you want to try to achieve, then maybe that doesn't fit very well into the RL framework. But if you have a goal, then super framework to work with. Especially since it has actually been proven to work really well. So here is a sample of the most successful stories coming out of DeepMind when RL was basically run at scale. So as you can see, there are a lot of examples of games and video games. So for instance, the seminal work on Atari, the work on Go and StarCraft and Stratego. But as I said, RL is not confined to games. It's about trying to achieve a goal. And so here, like on the bottom row, there is AlphaDev and AlphaTensor, which were used to discover new algorithms. And the bottom on the right is basically RL was used to try to control in a tokamak the shape of the plasma to get better nuclear fusion reactions. So you can see, it is a very general setup. Now, I had myself the luck to spend my days on AlphaGo and its descendants. This is what I call the zero series. Especially from, AlphaGo 0, we showed that we could train an agent to master domains. And when I say master, I actually mean, being the world champion hands down at the time when those things came out. And we learned to do that without any human input, information, or you basically learned everything from scratch. And so I want to talk to you about the zero philosophy, which I think is a great philosophy for research. And it's about this. So if an agent can learn to master an environment tabula rasa, so without any information, then basically you've demonstrably shown that you have a system that is able to discover and learn new knowledge by itself. This also means that this algorithm is general and should apply to other domains. And I think like the ability of being able to discover new knowledge, this is particularly important to advanced science, because a big part of doing science is to just explore areas that are not yet well understood and advance knowledge. And you need to accumulate knowledge, continuously generate and discover new interesting truths. And that's a huge part of doing science. So, like, especially for research, I think this is like a great way to demonstrate that you can discover new things. I would say that especially now with the big success of LLMs, maybe a more pragmatic point of view is to be able to start at a certain knowledge base, and then you want to know that your algorithm is going to continue to discover new things from there. So you don't really need to start from zero. What you really need is to have this algorithm that can discover new things. And we've demonstrated that you can do this with this research and these AlphaZero things. So let me go into some kind of examples. AlphaGo Zero and AlphaZero, as I said, they learn simply by playing against themselves, starting completely from random play. And what we observed is that they basically rediscovered human patterns, accumulating thousands of years of human knowledge, maybe in a matter of days. But ultimately, some of those patterns were kind of discarded in preference of new discoveries that humans don't even know about. They don't even know about. So in Go, I believe that AlphaGo basically starting a new move at move, I would say move 5, a move that wasn't even played by humans. And I've heard, if I'm not mistaken, that Magnus Carlsen was saying that because his coach was really good at using engines and he got to use AlphaZero-like engines when those came out, he got a big advantage momentarily over the other chess players, because basically these things was playing very differently, and people were not used to it, and they didn't know how to handle those new situations. So that's kind of Go and chess. And actually, if you look at, for instance, the figure I showed on the bottom right, this is this is trying to show the frequency of AlphaZero playing that particular pattern called, for instance, the Caro-Kann defense. And you can see that it basically discovers it after 2 hours of training. It plays it for about 4 hours quite consistently, and then this kind of pattern starts to disappear from the games AlphaZero is playing, probably because it has found kind of a way that makes this pattern not very interesting anymore. While on the bottom, the Queen's Gambit seems, the frequency at which the Queen's Gambit is played is just increasing over time, over training time. All right, now let me talk about Alpha Tensor. And so this was a work that was trying to find what is the best way to multiply two matrices together. And so maybe the naive algorithm that you may have learned at school requires kind of n-cube operations when you're trying to multiply two n by n matrices. So for 2 by 2 matrices, you need 8 multiplications. For 4 by 4 multiplications, you need 64 multiplications, etc., etc. So there was at some point a big discovery from a person named Strassen that found that for 2 by 2 matrices, actually you could do it with only 7 multiplications. And he also showed that this was optimal. You couldn't do better than that. But as soon as we went to 4 by 4 kind of matrices, basically we knew nothing more than applying Strassen algorithm twice. And so, still reduces from 64 to 49 multiplications. And so in Alpha Tensor, we try to discover a new, efficient, and provably correct algorithm for basically tasks that look like matrix multiplication. It actually did. It found new things in actually many different sizes, discovering like brand new knowledge that human never known about. And so, if you had only trained on what human had known, then you would have never discovered those. As a big bonus as part of this work, we showed that basically, we could basically AlphaZero could tackle huge action spaces. So as I wrote here, 10 to the power 30, but basically for practical purposes, this is just infinite. And so all those successes, Go, chess, tensor decomposition, are all specific to a certain task, if you will, a certain level. But under the hood is basically the same AlphaZero algorithm that is running and making those discoveries. And so what we had in mind is like, is there an environment that captures a much broader class of tasks that are relevant for science? And you guessed it, our answer is yes, it's mathematics. But just before we get there, the lessons we've learned from those from all this work. So what made those systems superhuman? I've listed up what I believe are the four most important properties. First is to scale up trial and error. And basically to discover new knowledge, you need to try something new and be able to learn based on the feedback you receive. And if your feedback is not grounded, if you invent your own feedback, then it's really, I think it's really hard once you venture out of what's known. And so you really need a way to measure if you are achieving your goals or not, where you are in the, where are you in your solution, etc., etc. Also, AlphaZero uses a lot of search, and it's my belief that search can really accelerate the discovery of new paths and skills. And it's because most of the time, when you sample, a different action, not the action that is that has the highest probability. If you try that action, most of the time it's going to be bad, but sometimes it's going to be good, and you need to discover why that action might be good or not. And so you need to follow up on kind of playing well after you play that action. And I think, for instance, AlphaGo and MOOC 37 is a good example of that. It had a very low probability of being played, but it was still explored in the search, and then it was discovered that it was a really good move. And so it became, it was played, and it was described as being very creative. The final one is you need to have a good curriculum to take you all the way to superhuman. And in the AlphaZero case, in Go and chess and shogi, we relied on the fact that it was a two-player game, and so you could do self-play. You basically always have the right opponent to play against, and that was really important. Okay, so now let me try to connect those two. Scaled up trial and error. We have, Lean is the environment to explore mathematics completely in silico, and the algorithm is going to come from AlphaZero. Again, Lean is going to give us kind of this grounded feedback signal. It's going to tell us, what have we proved so far, what's left to be proved, and it's going to tell us when we are done, when we get a correct proof. For search, we can rely on AlphaZero's search algorithm. It works pretty well. And maybe kind of the question mark is, what do we do with the curriculum? In some sense, where are the levels coming from? But so you've understood kind of the idea of AlphaProof is to use AlphaZero for mathematics, and in particular, formal mathematics. So, let me make kind of a napkin kind of master plan for AlphaProof. So Lean gives us a way to scale up trial and error with an environment to explore mathematics completely in silico and a perfect feedback signal for proving. And then now, if we extrapolate from the work we've done in the other domains, I conclude we can therefore reach superhuman intelligence and discover new truths, just like in Go, chess, tensor decomposition, provided we can generate high enough quality and quantity of problems, and RL works. So I'm very bullish on RL works. And so, as I said, the question that remains is, how can we generate high enough quality and quantity of problems? Where do the problems come from? And so I think one of the answers has to be that, the problems partly comes from the humans. And maybe the most important reason why is that it's because we want to help human mathematics. We could try to create alien mathematics, but really what we would like is to help human mathematics and kind of contribute in that community. And maybe a more pragmatic reason is that humans have already come up with a lot of problems that are quite interesting. But of course, we shouldn't throw away the second part where AlphaProofs would define the problem. And so I think there is maybe two ways to slice this. One is AlphaProof defines a problem around human mathematics. And we've done a little bit of that already with auto-formalization and test MRL. So it's perfectly fine if you don't understand what I mean here. I'll try to explain those a bit later. But the other part is basically really augmenting human mathematics. So, ideally, AlphaProof would be able to discover new areas of mathematics, build new theories, etc., that humans find interesting. Yes. So these are maybe where the problems can come from. So before we move on, I want to take a step back because if we're thinking about AI for mathematics, there is potentially a choice. There is a choice of doing it in natural language or in formal language. So I've been arguing a long time now for the formal part, uh, but actually most effort in AI at the moment is on informal mathematics or doing basically mathematics in natural language. And the reason why is because basically all of the data of mathematics, by many orders of magnitude, is written in natural language, of course. So you have this mathlib library that is growing and that contains quite a lot of math, but it's still a few orders of magnitude smaller than the amount of mathematics you can find in textbooks, on archive, on published papers, etc., that are all written using natural language. So that's kind of the trade-off you get when you use formal mathematics is you really have a very small amount of data. That's when, again, you bump into the question of how do you get the problems where the problems come from. However, I guess it's my opinion that because natural language mathematics, at least the reasoning part, is not verifiable, I believe that this is an issue if your goal is to build a system that can go beyond human knowledge and create new knowledge. You can, of course, improve the reliability of those systems. But the problem in mathematics is really that if you build on any false statement, then it destroys everything you do afterwards. So you really need like 100% reliability. That's a property of mathematics, and that's why I think that verifiability is very important. And basically, Lean is already superhuman at verification. And I say all of this for mathematics, but actually I believe this is true for many important, impactful applications that we cannot solve yet, and scientific problems in particular. So in the domains we cannot solve, there is almost by construction there isn't much data available because the domain is relatively poorly understood, and maybe it could even be a completely new domain that has just been discovered. You could also have applications that are somewhat niche, and maybe if you think about what AGI would do, you could argue that maybe mathematics is a bit niche, but it's still extremely impactful. And it's conceivable that generalization from all the other data would be somewhat limited. And so if we are data scarce, we really need a process that can continuously generate and discover new interesting facts that are not yet represented in the data. And you need a way to ground those new facts so that you can check that you are basically constantly adding new truths and building on top of new truths. And so this is really AlphaProof's foundational bet, is that perfect verification will in the long run be the most important property for mathematics. Let me recap. RL meets formal math. So we have a proven recipe to build agents that can discover new knowledge by themselves and reach superhuman intelligence in certain domains. The key ingredients I've highlighted are scaled up trial and error and grounded feedback. And basically formal math provides us with those key ingredients. So these are the big ideas that behind AlphaProof. So now let me talk to you a little bit about the IMO and our participation in 2024. So first, what's the IMO? The IMO stands for the International Mathematics Olympiad. It's basically the world championship level event in mathematics that brings together the best young minds from around the world. So every country brings their top 6 high school students, and they try to solve 6 problems in 2 sessions of 4.5 hours. So basically, in total, they have like 9 hours to solve 6 problems. In these 6 problems, there are 2 easy problems, 2 medium problems, and 2 hard problems. So let me first try to illustrate what it means to take the top 6 high school students for the USA. So let's say there's about 17 million high school students. It's not like kind of every kid loves math and is going to do a math competition. They might instead play video games and maybe in the future actually build the math library of the future. But anyways, at the moment, there's about 60,000 of them that participate in these AMC competitions. If they do well and they are still kind of into this, they might go and participate in this AIME competition. And so for those of you who've been following kind of the benchmarks that are used in AI, you may know about this math benchmark that basically contains a lot of AMC and AIME problems. And so the reason why is that basically AIME, what you need to do in the AIME is to, the solution is always an integers between 1 and 1,000. And so, it makes it easy to check whether kind of your system has outputted the correct answer or not, like the correct number. You can check that very easily and kind of use that as a grounded feedback. The problem is it doesn't tell you whether your reasoning to get there is correct or not. Now, like if you need to guess 177, then I think, I still believe that it's more likely that you have correct reasoning when you come up with the right answer. And so, that might still help to improve the reason. And it's basically what's happening. It's improving the reasoning of those models. But anyway, when you do really well at the AME, you may participate in the USA Math Olympiad. There's only 250 now. Then if you are in the top there, you may go to the IMO camp. And from there, only the top 6 people are selected. So you can see there is like basically 6 or 7 orders of selection. And I'm told by my colleague who did the IMO for the UK that they study for 1,000 of hours, maybe an average of 3 hours for 3 years. So really intense training for this competition. Now let me share a little bit about the problems. And I'll start with this quote from Po-Shan-Loh. So Po-Shan-Loh is not anyone. He's not new to the IMO. He was actually the coach, the national coach for USA for the last 10 years. And he said, I tried this year's problems while at the IMO. It took me hours. And context about the IMO, problems are specifically selected to be non-standard. So during the IMO itself, national coaches meet to pick the problems to appear on the exam. One of the most important tasks of that group is to avoid problems similar to problems that appeared anywhere before. And so they go through a great lengths to ensure this. And so that's why basically we really wanted to, we picked the IMO as a goal for us, is because we thought there was really a test of reasoning and not of knowledge. And like, as Po-Shan-Loh says, even for specialists, even for the national coach of the USA that's been doing this for 10 years, it will take him hours to solve those problems. The final property of participating at the 2024 IMO was that those problems were not leaked, right? And so you really needed to kind of be able to reason to solve those problems. As I said, there are like easy, medium, and hard problems. Easy is, in fact, those problems are not easy at all because only half of the participants solve 2 or more problems. And so, like you take the top 6 from each country and half of those won't be able to solve the easy problem. All right, so now let's go really to, this IMO 2024. And I'd like to relive a part of it with you. So, we had contacted the IMO organization, and we had agreed with them that they would send us the problems. We had contacted some judges, also part of that competition, so they could grade our solutions, and we tried to participate. So I just want to make sure, I clarify exactly what our IMO participation was. And I think a good way to think about it is more like an Apollo program. And so what we really wanted to know is, can we actually reach the moon? Can our system solve the 2024 IMO problem at all? Given the compute that Google can give us at that time and enough time for doing reasoning. So it was really about this, like, can we build a system that can solve those problems at all. And I think at the time when we got started, it was believed that this was like 5 or 10 years away. Okay, so now let me take you to 7 months before January 2024. So we are 7 months away, and we need to make a decision about geometry. So why geometry? Is because MathLib is very sparse in 2D Euclidean geometry. It doesn't have much of what you need to know about Euclidean geometry, mostly because researchers don't really care about 2D Euclidean geometry that is useful for the IMO. And so we're a bit unsure what to do. We are debating whether maybe we actually don't do geometry at all, or we try to fill in that part in MathLib so that our agent has the basic knowledge that is expected every student to have. And so we are debating this when miraculously another group within Google DeepMind turned out to have been working on exactly the IMO geometry problem, and they already have a system that is very, very strong. Their system was already approaching gold level medal performance on the geometry problems. And we learned about that because they published a paper in Nature in early January 2024. So miracle, but we decided to join forces with them for July. And so Alpha Geometry will tackle geometry, and AlphaProof will tackle algebra, number theory, and combinatorics. A couple of months later, we are debating another thing. So we've been training AlphaProof on proving theorems, but not all questions are on the form prove that. Actually, some require an answer to be determined, like find or x such that, and this is not just an integer like the ANE. It could be, it's the set of, these numbers that have this property, etc. And so it's actually not obvious how to do well in formal language, because you have like this kind of tautological case where, it says, well, what are all the x such that property p holds? And it says, well, it's the set of numbers where p holds. And you have like a really easy time to prove that, but that's definitely not what kind of the judges were after. And so actually, the answer itself is a bit of a subjective thing. And we debate, what we should do. Either we do what's was known outside as the easy mode. We basically feed in the correct answer to AlphaProof, and we ask AlphaProof to prove it. Or we go with hard mode, where we try to determine the answer. We have something that determines the answer, and we prove it. I personally don't really like easy and hard kind of keywords here because it's fairly well known that kind of the bit that is the hardest for the IMO is the proving part. It's not really to guess the answer. But anyway, so we are debating. We're not sure exactly what to do, but after thinking about it through, it's pretty clear that we need to do hard mode. And what's cool is that actually kind of guessing the answer is exactly what kind of Gemini is being trained on. And so we decide that we will generate candidate answer with Gemini, and we'll attempt to prove and disprove all possible candidates with AlphaProof. So that's how we're going to participate. Now, the final thing we are debating about is about kind of the input that the system should receive. Should it receive the natural language description of the problem? For instance, in English. If you participate at the IMO, you can choose the language in which you will receive the problems. Not everyone has to read it in English. You can have it in Russian or in Chinese or in Japanese. You can choose your own language. Unfortunately, they don't propose Lean as a language. And so we're debating whether we will send kind of English to the system, or we'll ask our experts internally to manually formalize the problem and send that as an input to the system. And so we debate this a little bit with our judges, and very quickly we have the same opinion, because what we really care about is the mathematical reasoning and problem solving at the IMO, right? And that's what we are there for, not really about our capabilities of actually translating the problem in formal language. And so we decide that it's okay for what we want to achieve, that we will give the formalized problems as input. And so we ask our Lean experts to manually formalize the problems for the system. So if I recap, our protocol is going to look something like this. So we are going to officially receive the problems at 1 p.m. the lean experts will first manually formalize the problems. And then that's where kind of after that, the AI comes in. So we'll generate hundreds of answer candidates with Gemini. AlphaProof will try to filter all the easily disprovable ones. And then we are going to run test time error. So again, I haven't told you what is test time error, but I'm going to get there. Okay, day one, we are there. Tuesday at 1 p.m. we receive the problem. P1 is an algebra, P2 is a number theory, and P3 is a combinatorics. And P1, P2 actually requires an answer to be guessed. And so, we ask our experts to manually formalize the problem, then Gemini to guess answer candidates, and then we get AlphaProof to try to disprove all those answer candidates. And so we have already very good signs, is that AlphaProof is able to disprove 99% basically of guesses for those two problems in a matter of minutes. And so this is a really good sign, because we've observed in the past that when AlphaProof understands the problem, it's going to be able to disprove a lot of kind of false candidates. But for problems that it doesn't understand at all, it wouldn't be able to disprove much at all. So that's really good sign for day one. On day two, right, we receive again at 1 p.m. The problems. We knew actually that P4 and P5 had to be geometry and combinatorics, because there is a rule that the easy and medium problems, all categories have to appear in easy and medium problems. But we are pretty happy to see that P6 was the algebra functional equation, because we knew that also AlphaProof was particularly strong in functional equation problems. That said, P6 is in the hard category, and so, it's the hardest problem. So even if it's kind of a good category for AlphaProof, nothing is guaranteed at all. Turns out that alpha geometry is able to solve the geometry problem, I believe, in seconds. So really powerful. It get there. So basically, they came in, they run that thing for a few seconds, and then it was done for them. The P5 combinatorics was actually very tricky, and our human experts failed to formalize that problem on the day. And the P6 algebra, it also requires answers to be determined, and Gemini generated a bunch of answers. And when we AlphaProof tried to disprove it, it could only disprove 7% of guesses. So it doesn't have zero traction on the problem, but it doesn't have probably as good an understanding as on P1 and P2. All right, so day 3, Thursday, AlphaProof hasn't proved anything yet, but we had a way to track progress. And so we observed on the day 1 problems that P1, AlphaProof had actually solved half of the problem. And so actually in that proof, there are at least 2 ways to split that problem into. You'd case on the fact that something is either even or odd, or that it's rational or irrational. And so AlphaProof had kind of come up with these ideas of splitting this problem in 2 by itself. And for instance, in the even odd case, it had proved the even case and hadn't finished proving the odd case. It wasn't able to prove the odd case yet. In P2, when we look at it, AlphaProof had arguably solved the whole problem. So I don't know if you know, but in the IMO there is a whole section where after the competition is, after the students have submitted their answers, the team captains can argue with the judging committee that actually, this student has done this much, and so therefore they deserve that much points. And so, if we had followed that process, we believe that with whatever AlphaProof had, we may be able to argue for the whole problem. So let's say, 6 out of 7 points there. And then on P3, the combinatorics problem, AlphaProof hadn't made any progress. On the day 2 problem, as I said, alpha geometry had already solved in seconds that problem, so 7 out of 7 points. The P5 combinatorics, we had made no progress. I think by that time we had a formalization of it. But what was really cool is that actually on P6, AlphaProof had made progress and had proved a particular case that we now know is worth 2 out of 7 points. So probably on Thursday, it had actually made quite a bit of progress on all the problems, and we may have already have like about 18 points. Now, Friday, we received this email. That's there is the name of my colleague Rishi, but it's actually sent by AlphaProof. And AlphaProof is sending an email each time it solves one of the IMO problems. It says, I have discovered a truly marvelous proof of IMO 2024 P6, but this email is too short to contain. Of course, it's a joke, and the whole proof is there in the email. And so when we see that, we are extremely excited because we know we've kind of have P2, alpha geometry has P4, we're making progress on P1, and we have. It seems like it looks like we have solved the hardest problem, P6. So extremely excited. I run to my colleague's desk, Oliver Nash, who is one of our lean experts, and so we basically copy paste that proof into official lean, and it thinks a little bit and says, yeah, all good, proved. And so I run back to my desk. I don't think too much. I just forward that message to Demis and Sergey. So it's Demis Hassabis and Sergey Brin. Um, uh, and I wanted to share that for two things. One, I think it shows you the trust I have in Lean. If I didn't trust Lean, I would probably wouldn't have sent that email kind of seconds after kind of getting confirmation from Lean that this was all good. And the second thing, I thought a little bit after that is like, oh, was this like kind of a stupid email? But I think actually we are in a company where it's cool to do this. And Demis and Sergey were following a little bit what was happening during this competition. So um, uh, a little bit later in the day, actually, we receive another mail, and it's a full proof of P2. So now there is nothing to argue about. Perfect proof found by AlphaProof. And a little bit later in the day, actually on that same day, we also received a full proof of P1. So in conclusion, final results, P1, P2, and P6 were fully solved by AlphaProof, and P4 was fully solved by AlphaGeometry. We actually tried to keep running over the weekend in the hope of getting 1 point on P3, because actually the agent made some progress on it, but it turned out that it was not enough for a partial point. So we reached the score of a silver medalist and missed the goal threshold by 1 point. Of course, I just want to reiterate that we definitely use more time and more compute than was available to the human participant. I want to come back a little bit on this P6 problem, because it turned out that it was arguably one of the hardest problems in the last years at the IMO. Only 5 out of 609 of the participants solved this problem fully. And it's the top 6 people of every country who comes in, and only 5 in total solved the problem fully. Sir Timothy Gowers, who is Fields medalist and IMO gold medalist as well, he said that he actually spent a couple of hours on this problem and did not solve it. And I find the fact that the program can come up with a somewhat complicated construction like this very impressive. So in no ways am I saying that we are close to Tim Gower's kind of math abilities, and he may not have spent these 2 hours really trying to solve this, and these things you need to these are kind of you need to practice to solve these things, and so in no ways am I saying that we are close to Fields medal level. But I think we all interpreted this as a really, really encouraging sign for the future to be able to do something really non-trivial. Let me conclude this IMO part with some of the challenges we've observed. The first is the gaps in MathLib. And so the most blatant one is geometry, actually. If alpha geometry was not there, he may have required us to actually completely write that part in MathLib so that we could do the geometry problems. Or we may have decided not even to try the geometry problem. Also, I want to say that even in P1, we observed that actually there were some gaps in MathLib that we suffered from. And so in one of the proofs where you have to prove that it's either rational or irrational, AlphaProof had proved the rational part, and it was struggling on the irrational part. So this is not definitive, but in fact, we observed that like the natural way to prove this would be to use a certain theorem that turned out to not exist in MathLib. So this is not an excuse. AlphaProof could have conjectured that theorem, proved it in line and used it to finish that proof. But it turned out that that problem was more difficult than it needed to be. Now, combinatorics problems were also very difficult. Just P5 was extremely hard to formalize. A lot of the necessary API to represent those problems about actually ironically about agents, environments, and strategies is not present in Mathlim, and that was made that problem very hard to formalize. And the reality is that even when we had formalized it, we did not manage to make progress on P3 and P5. So combinatorics were difficult for AlphaProof. And of course, we use many orders of magnitude more compute than human contestants. In some way, I think we actually successfully landed on the moon. I think that is actually the important part. And we will want to be more efficient for the next trip. All right. So now let me go into the methods. And before we get there, I want to remind you that when we're talking about the methods, there were two important aspects we needed to think about. One is, where do the problems come from, and how are we going to have an agent that learns to prove those problems? So we trained several models. One model is a formalizer model. So it takes as an input a problem described in natural language, in output a lean formalization. So this is based on the idea that we are going to lean onto human-defined problems instead of inventing our own problems, and we are going to try to translate them in lean, because they all exist in natural language, but they don't exist in lean. So we're going to try to do that. Trying to do that with humans don't scale at all. It takes a long time, and so instead we want to try to train a model that can do this automatically. Okay, that's the formalizer model. And now we also have a prover model. So the architecture of a prover model is that it takes this kind of, if you remember in my demonstration before, this kind of yellow box, the tactic state, the lean state, that tells you, what do you know now, what do you need to prove? This is the thing we're going to send as an input to the prover model. And then the prover model is going to sample n continuation for the proof. This n things you might consider potentially part of the proof, and alternatives. And then you take this prover model and you put it in the AlphaZero search. So you're going to search over actions, which are basically one line in the proof. Each time you add one line in the proof, you send that to lean, and lean tells you, what do I know now? What do I need to prove now? And that's basically how the search works. If you know a little bit about AlphaZero and MCTS like search, they try to exploit, what kind of the networks tell you, the neural networks tell you. They exploit the high prior and high value paths, but it has a mechanism also to explore low visited paths. For instance, that's how move 37 in AlphaGo is discovered. Is because it might have a low prior and might not be considered the right move by the network, but we're still going to try to visit it in case it might be an interesting move. Okay, so now let me put this thing together in the pipeline. Step one, we do auto-formalization. So we train a formalization model and auto-formalize human-created problems. So this is really the answer to the question where the problems come from around human mathematics. And here I want to highlight a few advantages of using kind of formalization of a problem. First is that when you send the problem to Lean and Lean says this is a valid syntax, it means that your question makes sense. It's not kind of something that doesn't make sense. So it's either true or false. You've generated something that is either true or false. Okay, the problems might not be interesting. They might be trivially true or trivially false, but they are either true or false. And so one way to see this is you have the human problem in the middle, and you try to generate kind of lean kind of variance of it. If your model is really good, then it will do the perfect translation. But maybe also it will generate problems kind of that are kind of look like that problem, right? And so when we have this formalization model, the way we used it is we were able to gather about 1 million informal problems. And there's a lot of problems to train for the IMO, about 1 million of them. We pass them through our formalized model, and we generate roughly for every problem described in natural language, we generated roughly 100 possible translations for it. And now we've just created a huge database of formal problems. Okay, now we need to have we need to train the prover to be good at proving, and so that's where you don't really want to be completely in the alpha zero philosophy where you really start from scratch. Here you want to be pragmatic and you want to start with something that is already can do a few things. So you take a pre-trained model. In our case, it was pre-trained on a lot of code. And then kind of the next step is you're going to train the prover model supervised on MathLib. So MathLib has about like 100,000 definitions, 200,000 theorems, 300,000 lines of proof. And basically you are really going to do supervised. So, you are going to place yourself inside of a human proof. You're going to look at what is the mean state there. Then you're going to look at what the human said was the next step in the proof, and you're going to train the model towards it. So in some sense, very similar to regular kind of pre-training, but you get much more information from it. And so when you've done that, your prover model has learned a really good prior over, the actions to take. Unfortunately, MathLib is about, I don't know, but especially if you want to do the IMO, MathLib doesn't contain much IMO-like kind of problems. It's all about research math. And so if you take that proven model and you try to apply it on the IMO, you get around 0% solve rate on the IMO. I'm not going to say hard 0%. I'm not sure, but really close to 0%. And so that's why you start to have to discover new knowledge about how to solve those IMO problems. And so that's where you enter the next stage of the Alpha Zero reinforcement learning stage. And so you are going to train the proven model by RL. And the recipe is very simple. It's an RL recipe. For each formal problem, you're going to generate experience of either proving or disproving that problem by searching over lean steps. Once you've come up with what you think is a proof, you're going to use lean to verify the proofs. Lean is going to say this is not a proof, this is a proof. And for the things that are a proof, you're going to reinforce your proven network on those proofs. And so what happens is that, at the very beginning, the proven model is able to prove the easiest problems, really, really easy problems. It's going to learn from that experience and kind of climb the next rung on the ladder that leads all the way to IMO strengths, right? It's going to be able to then, solve a few more problems a bit harder. And by learning from those, it will go and get better and better and better and all the way to the IMO. And so for this stage, we decided to do a kind of really the Alpha Zero kind of pipeline, because what we wanted to see is that, of course we want to solve the IMO, but we want to do it in a way that we think will generalize way beyond the IMO. So, our real goal is to do real mathematics. It's not to stop at the IMO. So we want to have a method that is not tuned to the IMO. We want to have a method that can discover new knowledge. And so all these proving strategies for the IMO, this is completely discovered by the model by itself. So that's step 3. And then final step is this thing called test time RL. And so to give you a bit of context, as I alluded before, even for Poshanlo, the USA coach, or Tim Gowers or Terry Tao, the problems at the IMO are not obvious. So even if you have like a Fields medal level neural network of mathematical intuition, you cannot really solve those IMO problems instantly. Even for them, it takes hours to solve. And why is that? Is because those problems have been designed this way, and you really want to learn something about those problems. So it's almost like kind of a real scientific kind of experiment. You first need to think of experiments. In this case, it's like what could be true, what could be false. Then you need to run the experiments. Try to prove or disprove those problems, and learn from this experience to learn about that particular problem. And the way we did it is that AlphaProof is going to generate variants of the problem we are caring about. So in this case, we have these 6 problems at the IMO. These are the problems we care about. Can we generate variants of those problems? And basically then run RL exactly as in the previous step to try to discover knowledge, especially about those problems. So I've tried to illustrate this in some hyperplane where you have the agent and the problem. So yeah, try to imagine this a little bit. So on the bottom left, basically you have a bubble of problems that the agent can already solve easily. And so it's a generalist checkpoint. Every like little black dots here represent kind of a problem that the agent already knows how to do. And then, like very far on the top right, you have this very hard problem that you want to solve. So imagine maybe it's the P6 problem at the end. And so as I described, the first thing we did was we generated variants of that thing. So we basically explode kind of that problem into many, many variants. And if you are doing this well, you may hope that it will generate one variant that is actually already solvable by the agent. And so you solve that one, and you learn from that proof, exactly like before. And you learn a little bit about that problem, and then you repeat that process. You learn about that problem until you reach that problem, and you can solve it. And so that's how actually P1 and P2 and P6, all of them, require the standard route to be solved. Okay, so I want to finish this section with some challenges for AlphaProof. So we inherit some challenges from formal mathematics. As I said, most of human data is in natural language, but we started to have a good handle on how to translate that human data so that we could learn about it. So it's still a big challenge, especially as we move forward, but maybe we have some handle on it. Maybe something that is a bit harder is that we cannot easily learn and work on areas that are not supported by math. So for instance, like in the geometry case, well, if you have nothing about it, right, you can't even express kind of, the geometry problems that humans have come up with. And so that's kind of a real challenge to think about. And so this could be solved if you start to understand how to do creative building of new objects and theories. You understand interestingness and beauty in mathematics. But this is definitely kind of a really cool challenge for future work. Cool. So what's next for AlphaProof? As I said, like kind of from the very beginning, actually, of the AlphaProof project, the idea was to try to see if we could, learn about mathematics and potentially go beyond human mathematics. The IMO was a really, really cool milestone that I think was extremely correlated with that goal. But that's not where we want to stop. So obviously what we want to do is we want to broaden to the entire mathematical landscape. We don't want to be stuck at high school mathematics. We want in the future to be able to contribute to the frontiers of research math. And going back to the understanding that the Greek got 2,500 years ago of the importance of proof. It would be fantastic if we could democratize kind of this idea of a proof and share that with every thinker, from an elite mathematician to any other person. And so, can we have AlphaProof as a useful tool for every thinker? I want to conclude saying that the big ideas, they are really important, but equally important, if not more, is the people you are doing this with, and the mindset that everyone has on the team. I was pleasantly surprised to hear that in mathematics as well, you need to be really optimistic. Otherwise, you will never be able to prove anything. I think this is also true in AI and machine learning. You need to be absurdly kind of optimistic to be able to achieve kind of absurd goals. And really, individually, this was almost impossible. But we had this belief that together, it was impossible to fail. So these were the team members that contributed to this amazing project. And yeah, let me conclude that. And thank you for listening.